Hello and welcome to this third example of where we can apply second order differential equations in engineering. And in this third example, we're going to look at a series RLC electronic circuit. Just like our previous examples, I'm assuming that you've watched our introductory video where we talk about second order differential equations and how we can solve them. We're going to jump straight in here, and so if you've not seen that video first, it's worth going back and watching that before we start with this particular problem. Suppose we have a circuit that looks like this one here. It's a series RLC circuit. We're not going to go too deep into electrical theory in this video. We're just going to apply the principles of second order differential equations. But let's say that we have an equation, a second order differential equation that looks like this to represent the current in this equation. So we have three components in our circuit. We have an inductor, which is given the letter L, a resistor R, and a capacitor C. And the current in this particular equation is given by L d squared I by dt squared plus R di by dt plus 1 over C I, and that's equal to 0. So what we have here is a second order differential equation in terms of current I with respect to time t. And let's suppose that we're also told that the inductance in this particular circuit is equal to 0.2 henries. The resistance is equal to 330 ohms, and the capacitance is equal to 20 microfarads. Let's also suppose that we're told that when time is equal to 0, t equals 0, the current is equal to 0. And also the differential of current, the first differential di by dt, is equal to 30. And the objective here is to solve this particular second order differential equation for I. We're looking for an equation that looks like I equals. And what we're going to do is begin first of all by forming the auxiliary equation for this particular second order differential equation. And the auxiliary equation is going to look like this. We have L m squared plus Rm plus 1 over C equals 0. Again, if you're not sure where this auxiliary equations come from, it's worth watching that first video which explains this in a bit more detail. But we also know the component values for L, R and C, and so we can substitute those in here. And so we end up with something that looks like this. We have 0.2 m squared plus 330 m plus 50,000. 1 over 20 times 10 to the minus 6 gives us 50,000 in that case there. And solving this particular quadratic equation is probably easiest either using the quadratic formula or by using some computational method. We'll not cover either of those here, but whichever you choose, we find that the roots of this equation are equal to either minus 1481.22 or minus 168.78. And we see that both of our solutions are real numbers, but they are unequal. And we saw that in our previous video that this means the solution is presented in this form here. We're solving for current I, and that's equal to A e to the m1t plus b e to the m2t. That was the form that we saw in our introductory video there. And in our case here, we know two values for m1 and m2, and so we can substitute those in to say that I equals A e to the minus 1481.22 t plus B e to the minus 168.78 t. What we have here is our general solution, and in this case we have the solution in the correct form, but the two constants A and B are unknown, and so to try and find these we're going to substitute the initial conditions we were given. So we were told that at time 0 the current is equal to 0, And so we can substitute for I and t in our general solution here, and we'll see something like this. We have 0 now equals ae to the minus 1481.22 times 0 plus b e to the power minus 168.78 times 0. Well, both of those exponential terms raised to the power 0 are both equal to 1. Anything to the power 0 is 1. And so we simply reduce that down to a plus b equals 0. So we have an equation in terms of a and b, but it doesn't tell us what a or b are equal to. It does suggest that the magnitudes of a and b are equal, but with an opposite sign if they add together to equal 0. But what we're going to do is find some additional information by differentiating the general solution that we saw before. And so rather than I equals a e to the power minus 1481.22t plus b e to the power minus 168.78t that we saw before, we're going to differentiate this equation with respect to t, and so we'll end up with di by dt is equal to minus 1481.22 a e to the power of the same minus 1481.22 t plus minus 168.78 b e to the power minus 168.78 t. The reason we've done this is because we can revisit our initial conditions again, because remembering we were told that when t equals 0, we were also told that di by dt is equal to 30. And so substituting in here for di by dt and for t again, we have something that looks like this. Remembering again that these exponential terms raised to the power 0 will all just evaluate to 1. And so we can just remove those. And we're left with something like this. 30 equals minus 1481.22a minus 168.78b. So we now have two simultaneous equations in terms of a and b, because earlier when we substituted into our general solution we had this one here, 0 equals a plus b, and now we've just found this second equation here also in terms of a and b. And these equations are most easily solved probably using a substitution method. Since because a plus b equals 0, we can say that a equals minus b. And we can substitute into the second equation, because rather than the a term that we saw in that equation, we can simply replace that with minus b, since a is equal to minus b. And that simplifies down to this, and we find that we can solve for b equal to 0.02286. Knowing the value of b, we can substitute the value of b into either of the original equations, but particularly the first one, a equals minus b, a must be equal to minus 0.02286. So finally we can revisit our general solution, and we now know the values of these unknown constants a and b. We can substitute them to find our particular solution. And so we have current I is equal to minus 0.02286 e to the power minus 1481.22t plus 0.02286 e to the power minus 168.78 t. Since we've solved for I in terms of time t, just as a point of interest, we could plot a function to show the response of this particular circuit for current on the y-axis and time on the x-axis, and we see another instance of a damped response, similar to the car suspension that we saw in example 2, where an initial pulse of current returns to 0 over a short time of around 0.05 seconds or 50 milliseconds. So I hope you found this video useful as to how we can apply the principles of second order differential equations to an electrical example as well.